Hello again, and in this next session in the class, we'll talk about universal Kriging. You may notice, people that are somewhat familiar already with geostatistics, that I skipped the variogram modeling for now, and that's my experience has been that variogram modeling makes a lot of sense once you know a little bit about Kriging, although you do have to realize, of course, that in reality you would have to do variogram modeling before doing Kriging. So the second chapter in our book has a good summary of the various issues and methods of universal Kriging. If you would like to have a more broad introduction, I recommend the book by Pierre Covariance. Okay, so before looking at Kriging, which is a method of linear regression, let's look at the linear regression method that you already know about, which is ordinary least squares. So in ordinary least squares, we're assuming we have some data variables, and we would like to predict some continuous prediction variable. And so what we'd like to get is essentially a fit, which is then also going to be interpreted as the conditional distribution or the conditional mean of y given x. And so the derivation of this system, where if you take x, the information that you have plus a column with ones, your weights are going to be this vector beta, and your y are going to be this observation you have. And so the model is basically that you have a linear model and you add an error term to it. So if you then make assumptions that these are all independent variables and identically distributed observations, then you get this final equation here, which is the classical ordinary least square solution that we get by minimizing the least square error. So let's now look a little bit at what are the various assumptions that go into this derivation. The derivation is not necessarily so important, but okay, so here are the assumptions. First of all, the error random variables has to have zero mean and should be uncorrelated with your data. The error term should also not depend on the signal, which means the values of y, so that variance will not change based on the observations we have. And most importantly, the data variables should be linearly independent. And that's of course not the case in the spatial case, because we have spatial correlations we observe when calculating the variogram. Okay, so how do we do linear estimation in space-time? So here we have a simple problem on the left-hand side, where let's say we have three data points, Z1, Z2, and Z3. So this is now in space, and we'd like to know what's over here. We haven't measured anything here, and we'd like to we still stick with our linear model in Kriging, which is to say that we write the unknown or the estimate as a linear combination of our observations. So the question is, what are these lambdas here, these weight? And so if you think about it, if these are all distance d apart, then a simple idea could be do what is called inverse distance weighing. That means that lambda is some function of the distance. The further apart, the less the lambda is. And so I could also standardize that. That seems like an interesting idea, but it sort of misses a concept, and it's namely that we do have spatial correlation in our system, right? So we say, for example, if I'd like to estimate this point over here, then if I have a point here that's a data point, for example, this is a data point and this is a data point, then it's logical, of course, that this data point has more information about this one because of the spatial anisotropy than this point here, on average at least. And so that has to be somehow taken into account, which is not taken into account if you just look at Euclidean distance. Okay, so the smart ones among you may always say, yeah, but okay, that's fine. What we can do is use the variogram. Why is that? Well, the variogram is also a measure of distance. It's just a different measure of distance, namely that if I have, for example, anisotropy in one direction, for example, I have longer correlation in direction 2 and shorter correlation in direction 1, then all those that are at equidistant in those directions this guy should get essentially more weight, and this guy should get less weight. So instead of using 1 over the distance, I could use, namely, this is the distance, this is the variogram. What I can do is simply modify that distance with the variogram and calculate the corresponding variogram value. And so what you'll get here is that the variogram value along direction 2 is less than the variogram value at direction 1, and therefore we'll get a larger weight. So that's an improvement, but it doesn't tell the whole story because it doesn't really look at what happens between the data. So for example, imagine you have 2 situations here. And imagine there's isotropy, so this variogram doesn't now really matter. I'm back to using the distance. Then it's clear that these situations are very different. It would not be logical to give a weight of, in this case, it would be logical to give a weight of 1 over 3 to 1, 2, and 3, but here would not be. It'd be more logical to say that these have to share some of their weighting. And why is that? Well, it's simply because they're highly correlated. So for the same reason as we have correlation between what we'd like to predict and our data, we also have correlation that exists between our data, and that should be taken into account in order to determine those weights. So Kriging does that. And so Kriging would be more looking at a situation like this, or would be resulting in a situation like this where these 2 data points will share their weight and these will get a higher weight as opposed to, for example, the inverse distance solution. Okay, so this here summarizes now the situation. We'd like to do linear estimation in space-time, which simply means that we're going to write or estimate the value at an unobserved location as a linear combination of the observations that we have. So there were 2 principles that we talked about, which one is, in order to do that, we'll have to look at the correlation between our unobserved location and the other locations, which are data locations, and that we'll have to account for the variogram. Remember that if you have, for example, an isotropy and the direction of major continuity is in this direction, and even though that this is closer to that point, this actually may end up having a larger weight. So that's our idea of the variogram distance has to be taken into account. The second case where we use the variogram distance is to look at the redundancy of the information that's there. So these are somewhat isolated data points, and these are data points that are closer by. And if they're closer by, then we expect that they have higher correlation, and so therefore they should get less weight. And so these 2 principles we need to take into account in our Kriging development. So this is very different from ordinary least squares. For example, imagine that you have some unknown truth here at the left and some sample data in the middle. Then if you would perform ordinary least squares, and your function would simply be x and y, namely x means a coordinate in this direction and y coordinate in this direction, then you would simply estimate the weights on those 2 directions. You will find that you have fitted essentially a function. So that's the ordinary least squares. So this here function that we observe can no longer be interpreted as a conditional expectation simply because of the correlation in our data. Now there are more sophisticated fitting functions, of course. So here I have another example of using biharmonic splines to fit. But then you get something that's a little bit more sophisticated. But the problem, of course, is again, is what splines would we use? Do you really interpolate your data? And what is the estimation variance? Because the spline method is just a fitting method. It doesn't provide you any estimation variance. And so in Kriging, we'll be trying to achieve that essentially. Okay, let's first look at what's called ordinary Kriging. There's nothing really ordinary about ordinary Kriging. It's just these are names are given, and later we'll talk about other methods with different names. Simple Kriging, universal Kriging, and again, those names are just historical. So don't try to attach any meaning necessarily to them. First of all, we'd like just like, for example, you like to fit a linear regression model, or you'd like to estimate the mean by means of the arithmetic average. We'd like to have some kind of an unbiasedness in that estimator. And so unbiasedness, as you know, is simply saying that the expected value of the estimator is equal to the expected value of that value at that location. And so if you then plug in that this is equal to that weighted sum, and then use the property that the expectation of the sum is the sum of the expectation, we find this expression here. So that's the general expression. A more limited form of that expression is we assume that our expectation is essentially the same at all locations. So that is an assumption of stationarity of the mean. Now, we can't really verify that assumption. It's just an assumption that's theoretical, and that will lead to some essentially simpler equations, and particularly the ordinary Kriging equation will highly simplify. Later on, when we do universal Kriging, we'll not be making this assumption. So in that case, we're assuming that the mean has some special kind of form that is spatially varying. So we no longer accept that the mean is constant over space. So that brings us then to this decomposition that I mentioned a number of times. And this is the basic decomposition in all geostatistics. So it's somewhat of a special case, I'd say, because in reality, of course, if you say that a signal is a mean plus a residual, and then you would say, well, that mean I don't know, and we'll treat it stochastic, or means as a random variable, and the residual as a random variable. It's just that, for example, the mean could be just it's not a function of space. So that's a Bayesian view of it, because now we say we have some prior that we don't know its own distribution, and we add to that a residual, which then gives me that definition of my random function. So in geostatistics, as I mentioned, we don't do that. We take the mean to be constant and not random. So it simply means it's not a random variable, so you write as a small letter. And in more general case, of course, I say that that mean is not stationary, so it's also a function of x. But it's, again, it's a deterministic function. It's not something that is going to be estimated, that's going to be estimated in the same sense. So we're going to estimate this r here. Okay, so we have discussed the issue of unbiasedness and how I would like our estimator to be unbiased. So Kriging is a least square method, just like OLS. And so what we'd like also to do is to minimize the variance of the error. And so that's what's written here. Now, given that we have unbiasedness, we can reduce that variance to an expectation. So that's what's done over here. So now we have this error term here. So if I take this error term and I plug in my estimator, which is the linear combination of your data, notice that your data now becomes random variables. That is in order to do this derivation in expectation. So the notation is written slightly different now, where we say from alpha is 1 to n, and we take this guy and we put it inside this guy, and we just say that's kind of the weight is kind of here is -1. So we plug that in there, and then we use our model, or say that our z can be written as a mean and a residual term. So now we've redone that, and so that means now that we come to this, we plug that into this form, and that's what we get over here. So our z is now a mean plus a residual, and our z star is now replaced by this value here. Okay, so I can now develop that more by simply writing out all the summing. So that square of a sum would then, of course, involve this double sum over here. And the expectation of a sum is, again, the sum of the expectations. And so now you see that what we get in our product terms. So these are the product terms. And notice that this product term involves the location of the unknown, the unobserved, and this is the location of the observed. And this other product term has the location of the observables. And so there you will see that, okay, this is something that has to do with the data redundancy, and this has to do something with correlation between the data and the unknown. So we write that a little bit, and so then we have this condition here. So it looks a little bit different from the unbiasedness condition that we had before, but that's simply because, remember, at alpha is 0, so that the additional weight to the unknown is in there as well. So this is essentially, if you then look at this and calculate derivatives, then we see that we have a solution of a system which has a constraint to it, least square problem with a constraint, and so we will use the Lagrangian formulation where we create a new function that is our existing function, which is this whole term here, so that would be this term over here, and we add the Lagrangian constraint over here. And that's also why we like to write that as with the 0 here, then that term becomes nice and easy. Okay, so this is a classical solution. I'm going to go further now into how this is exactly done. This is really standard material in optimization. Okay, so now we're at the final system, Kriging system of equations, which is a linear system of equation. Since we have a Lagrangian parameter, we have now n weights that are unknown plus a Lagrangian parameter, and as you notice here, we have n plus 1 equations. So a number of important things to notice is that if you look at these equations, we see here again that product expectation of a product of two random variables. So this is a covariance. Also because remember that R has an expected value that is 0. So here again we have a covariance, and then here we have our unbiasedness condition, as you notice. And so if these means would be the same, then this is simply that the sum of weights is equal to 1. We can simplify that more if we make more assumptions. For example, if we say that the covariance, which is defined here, the expected value of x and Rx, so this is specific to these two locations. If we say that it's not really function of those specific location, but only function of the distance between those locations. So then we get this here. So this should, this should not be a prime. It should just be x. So we say that the covariance is simply only a function of distance. It's not a function of exactly the location where we are. And so then what we get is this here. And so now we notice something that we can recognize in terms of our discussion on inverse distance weighting. So we notice that we are looking at two distances, because remember, these are distances between two locations. And so here we have the location of what we'd like to estimate, and this is location of our data. So that's that one term. So that at least accounts for that variogram distance in terms of between the unobservable and the data. And this seems to account for the correlation that you have between our data. And so that will then account for that data redundancy. Out of the Kriging equation, we also get the estimation variance, which is this weird expression here. And I'll talk about that in more detail later. So you wonder, where do we get all these covariance functions? Well, that's why we need to calculate variograms and covariances. So here I have this copper data set, and I have now these covariance functions. And so in the next session, we'll be looking at modeling those functions. But you can already understand that all these covariances, which are now a function of distance, can be read off out of these graphs, because basically the x-axis is distance between any two locations, and the y-axis would be then covariance. In this case, it's the cologram, but you can imagine this is then the covariance. And so that covariance is a function of distance and is a function of the direction. So if I have different directions, then I may end up, for example, in this direction. Let's say here, I have a larger range, so then I end up with essentially a larger covariance than in a case where I have a shorter range. And so that will be, Kriging will use that information to assess data redundancy, for example. You say, well, what was all the big deal then with the variogram? I thought that the variogram was the one that we wanted because it doesn't involve the mean. And so what we do is essentially the way the Kriging works is that it does use the variogram. It's just that it converts the variogram information. So this is this function, variogram is a function again of distance, and it converts that using these equations, which involves the variance into the covariance, and then this covariance is then used in the Kriging equations. So here's an example of how this mechanistically, at least, is going to work. So what we have is we'd like to estimate this location. We have 3 data values here, measurements. And so the first thing I will do is look at the distance between this, say, data point 2 and the unknown. So this is a vector, right? This vector has an orientation. So if I want to look up the covariance, I have to look at the covariance for that particular direction. And it has a length. So that's our lag distance. So here, that's the lag distance between 0, which is the location to be estimated, and the data point 2 is that covariance, and that goes onto the right-hand side of that equation. Then, of course, I also have covariances between data points. So then I have this vector here. So this vector has a different orientation, so I have to use a different covariance or variogram to look that up, and it has also a different distance. So that is this guy here, which goes into our linear systems on the left-hand side. So this is then the covariance matrix, which on the diagonal has the variance, and then it also is symmetric, of course. And you have that, these are the weights, and this is my right-hand side. So we notice that in all of this, there's no values here. So you notice that I could write this down whether this is value at 1 is 200 or 1. It doesn't matter. So the Kriging weights are independent of the data values. They're only dependent on the correlations that are existing, and hence only dependent on the distances. So in SGEMS, which you will be doing for your homework, and also refer to the Universal Kriging tutorial that I have on YouTube, there will be a tab under estimation that says Kriging, where you can do various forms of Kriging. And so in your homework, you'll be looking at Kriging porosity for this particular groundwater aquifer system. Okay, so let's now talk a little bit about practical implementations and how this is going to work. So the first thing is we'll talk about is that is what's called global ordinary Kriging. So what does that mean? Suppose I have some unknown phenomenon and I have observation, and imagine I have modeled and calculated variograms. So if I want now to estimate something at this location, and what I typically will do is define what's called the Kriging grid. So it's a regular sort of spaced grid on which I will then perform all my estimations. And suppose we arrive at this point in global ordinary Kriging, what we'll do is we'll use all the data points to do the Kriging. And so imagine you have here, say, 50 data points. So that required then creating a 50 by 50 covariance matrix. So we solve that, we get a value, put that in that grid, and then we go to the next one. So in the next one, I'll use still the same amount of data points. And so the nice thing about doing that is that the covariance matrix does not change. Remember, the covariance matrix in the previous slides was a function of the distances between the data, so that does not change. The only thing that changes is the right-hand side, which involves the distances between the unknown and the data locations. So if you have, this works really well if you have very few data, of course, and because if you get an enormous amount of data, say, for example, that's the case in remote sensing. If you have gaps in remote sensing data, you want to interpolate that, there's just a million amount of observations, so you cannot invert that easily, that covariance matrix. But also, there's a somewhat assumption here of, again, the stationarity assumption is that data that we're using over here, sorry, at least in terms of mean and variances and variograms, are somewhat similar. If you, for example, have this part of the domain would be sandstone and this part of the domain would be shale, it doesn't make any sense to use this data because the shale data doesn't inform much of the sand data. So that is something that will not work well in this particular setting. So what we'll then do later is called local Kriging. Yes, so instead of using global Kriging, it's often in reality and practice more useful and desired to use a local Kriging. What does local Kriging mean? It simply means that I will define a search neighborhood around the points to be estimated, and we only use the information within a certain search ellipsoid or neighborhood. So yes, as I already said, this is going to be an ellipsoidal search neighborhood. And so that will have to be then user-defined. So we have an additional user-defined property. So, okay, let's do that. Let's say we have here global Kriging, and let's say now we do local Kriging. So that means that at every point in the grid, instead of using all of the information that was there, the 50 data, we use only those samples within a limited search neighborhood. So in this case, we're on a 100 by 100 grid, and so we use our search radius of 30. And so what you now start to notice is these kind of artificial features that are occurring, which look like faults or big changes into the estimation. And so that's not a desirable feature. These are artifacts that we'd like to ignore because evidently we're creating something that's very different in nature. So in order to get some fixes, let's analyze this problem a little bit more and why this occurs, because this is an important practical element of Kriging that we need to worry about when we're doing this in the real world. Okay, so here's a situation, let's say, where I'd like to estimate this point here. I have a search neighborhood that's simply a circle, and so what I'll do is, in terms of the Kriging system, I use only those 4 data points and ignore these data points. So you say, well, isn't that a problem, ignoring data points? Well, not necessarily, of course, because as you know, when you get increasing distance from away from the point that you would like to estimate, then any data will have a decreasing correlation. So it probably will be that essentially these data here will get very small weight. So why not just ignore them? So that's kind of the principle behind the search neighborhood. It looks like a good idea, but let's look at the situation here. So I have here 4 data points, and so 3 of them are relatively small, and 1 is very big. So if I'm now going to go to the next Kriging point, which is here, I have to move my search neighborhood, and as a consequence, this big value here is going to drop out of the search neighborhood, and so my estimate will be very different. It will only be determined by those 3. And so because this probably had some reasonable weight, you see that this data is distributed quite equally around the point to be estimated. It's very likely that this value will be a lot smaller than this value. And of course, that will occur even in this point and that point, so in the neighborhood. So you get sort of this discontinuity that is happening, and that's not desirable. So there's a number of fixes that are proposed to that. And there's some real simple fixes, and there are some that are perhaps a little bit more elegant. So here on the left-hand side, this is the fix that I often use, is that instead of using a search neighborhood, what you can do is simply not use a station neighborhood and say, I would also like to have a minimum amount of points in my neighborhood. What that does is that it sort of mitigates this problem that by the shifting neighborhood, that suddenly you have data that are dropping out of this. And so you can imagine also that if you start increasing this number to all the data, you end up being back at global Kriging. So in a way, in a sense, that way, if you do it that way, then what you're doing is that your search radius, your effective search radius, is dependent on where you are. So you'll have a different search radius or an effective search radius at different locations simply because you're using different amount of data in that search neighborhood. And of course, because of the configuration of the data, then sometimes that search radius or that radius may contain, that may be quite large, much larger than in another situation. Another elegant fix proposed by my colleagues Jacques Rivauer and Thomas Romary is to add a penalty to the diagonal, and therefore you're somewhat decreasing the influence of data that are further apart and sort of decreasing the influence of covariances that are of the diagonal, and that leads to the image that you see here on the right. Okay, let's now talk about Kriging or estimation variance. So as this quick recall, estimation variance. So for example, if I estimate the mean of a population, I can do that using the arithmetic average, which is here, simply that. And as you know from your basic stats classes, the estimation variance, which can then be used to create confidence intervals, is simply sigma squared divided by n. where sigma is the population variance and is the number of samples that you have. So what about applying that in our case? Well, if you would do that and you would calculate the arithmetic average of the samples in your domain, you can use that. That's still an unbiased estimator of the mean. The problem is that you can no longer use this formula because of this issue that you require the samples to be independently distributed, and that's of course not the case when you have spatial correlation. So if I then do Kriging and I've estimated my weights, and I know these values of lambda, what would then be the estimation variance? Well, just like with the least square estimation of the mean, this being the theoretical result, you get the same property here, is that you get this theoretical result. And so this result looks actually quite logical. So this variance, this equivalent of this variance, is the original population variance, so that's also part in here. But then what you're doing is you're subtracting this part from it. So what it means also, if all the weights are 0, then this estimation variance is simply the variance of your population, and so there's not much you can do with that. But of course, if the weights are going to be positive and this correlation is existing, then you're going to decrease this population variance. And so your Kriging variance will then decrease as you get more population and as you have more data that are being used to estimate something at an unobserved location. So what does that look like? Okay, so here we have a simple case. We have 29 data in this domain. Let's put on my pointer. We have 29 data in this domain, and we make a Kriging estimate. So this would be that estimate. You see that you get a high patch here because there's a high values there. So this is our Kriging estimate. So of course that requires knowing the variogram, but imagine that we have that variogram or covariance. So here we see the Kriging variance. So what's typically the case of the Kriging variance, of course, is that at the locations of the data, your Kriging variance is 0. And so that's pretty obvious. If you go away from the data, then your Kriging variance will start to increase until it is equal to the variance. So imagine the variance would be 1. I think this is being standardized, but imagine the variance is 1, then obviously away from the data points, you get your variance back. And as you go away from data once you start subtracting that part. The Kriging variance is, as you notice, is not such an interesting, useful information per se. Be careful to interpret that really as an error variance in the sense that it's really a measure of how you're close to the data. So obviously in this area, we're far from data. In this area, close to the data. So you could say, well, I've got to figure this out on my own. I didn't need to do Kriging, and that's possibly the case. So this kind of Kriging variance is useful as a measure of how far you are from the data. One thing you notice with the Kriging variance here is that it's independent of the values of this information. So this information here, the exact values are never used to determine the Kriging variance, and that makes it somewhat limited in terms of its application. Okay, so I showed you in the previous slide that you can estimate the mean of your data, and then the question is, what about Kriging the mean? Because the mean is just another unknown, and we can say, I'm going to write my mean, my ordinary mean, my estimate of my mean. I can use the arithmetic average, and that's an unbiased estimator, but can I do better? And what would be then that variance of that estimator? And so the way that is done is exactly the way as Kriging, is that you solve just a different system of equations, and so once you have that, you can then derive what the Kriging variance is and get a better, sort of more appropriate estimate of the error variance of the global mean in your domain. And that can be quite useful. For example, imagine that you have a certain domain, could be an irregular domain and volume, 3D volume in which you have samples, and you'd like to know the global mean of that domain, how much stuff is in there on average in that domain. And so this is a way you could do that. And then you can also calculate the error variance. So if you have a pure nugget effect, then that error variance will simply resort back to our classical solution, which is sigma squared divided by n. Okay, let's move to different forms of Kriging. So in ordinary Kriging, in particular when you use local ordinary Kriging, we're sort of admitting that we don't know the mean, and it is also locally varying. In global, in simple Kriging, you say that essentially say that you know the mean, which is m, and that global mean is also constant stationary. So in that case, the mean now acts as another information source next to, say, the n data points that you have. You now have n plus 1 data points, which is the mean. And so in simple Kriging, then we plug in that mean. So we say that the residual estimate of the residual is a linear combination of the estimate of this residual. So now you notice that this m is known, so I can calculate this residual. And so the Kriging estimate is then simply you put this m on the other side, you rework this equation, and you find out that here is our classical ordinary Kriging estimate. But now what we have is we have an additional part to it, which is the mean. So what we're doing here is we're giving this weight to the mean and this weight to the data. Notice that now I don't have this unbiasedness condition anymore because, of course, I know the mean, so I know what the expectation is. So this is always unbiased. And so this is no longer equal to 1. So if this would be equal to 1, the unbiasedness part, in ordinary Kriging, then you notice this whole term drops out, and then I get back to simple Kriging. So because I have no unbiasedness condition, I have a simpler system of equations, namely I have only n equations and n unknowns. I no longer have a Lagrangian type of system. Okay, so then we come to possibly the most general form of Kriging, which is called Kriging in the presence of trends, or also called universal Kriging. So in universal Kriging now, we're no longer making an assumption that our mean is constant or that it is unknown and constant. We're admitting now essentially that our mean is varying with location. So the mean is now stationary, non-stationary. So these were remember our ordinary Kriging and simple Kriging equations. So in universal Kriging, basically what you're going to do is build a regression model for this mean. So what we have here is this mean. We're going to write this as a linear combination of function. And some of you have maybe seen this before. This looks a lot like ordinary least squares problem or a generalized least square problem. So essentially what we have is that these functions we are known, but the coefficients are unknown. For example, I may know that there's a depth trend, and I may want to include that information. So what I write here is this m as a function of depth, and so this becomes simply which is xyz, becomes now a0 plus a1 times z. So we always have the constant in here. That's why we have L is 0. So f of 0 is equal to 1. I didn't put that in here, but that should be noted. So we always have that constant in that regression function. So once we accept that, then I know now I have a definition of what is the z of x, which is m of x plus the residual, and this m of x has this particular form. Okay, and then I can derive the same equations. And so I have now more constraints. Now I have all these constraints to get unbiasedness. I have more complicated constraints. So remember, essentially in the ordinary Kriging case, this sum of lambda beta was equal to 1. So that would be the case 0 case. Remember that f of 0 is 1, so I would have the sum of lambda beta equal to 1, and I would have ordinary Kriging. If I have more of these functions, then I have more constraints, and then it increases my amount of Lagrange multipliers, and so I will have to solve a bigger system of equations, namely n plus the amount of constraints that are there. You notice that in the previous universal Kriging equations, there was no AK. And so that AK, that's dropped out in the derivation of the Kriging. So what about the AK? Well, the AK, remember, are the ones that are defining my global mean, or my means, or my locally varying mean. And so just like Kriging of the mean, the total mean, which we do in ordinary Kriging, we can now also Krig the trend function, because the trend function is essentially the mean itself. And so we can estimate these coefficients through Kriging, just like we estimate the global mean through Kriging, and that would give then, so here we have this estimates, we write the estimator of these coefficients, and that will be then a function of our data. And so that these are the various equations that we can derive from it. Okay, so here we have our overall then universal Kriging procedure. So first we define those trend functions. For example, it could be a linear trend, x, y, or z. It could be also quadratic trend. So once we have defined that, we have to estimate that trend. So that could be done using ordinary least squares. So that gives us some initial guess of the trend function. From that, we can then subtract at the data location that trend value. And so that's done here. And that allows us to compute the residuals at the data location. So once we have that, then we can compute and model the variogram of the residuals, and that would then have to go into solving into universal Kriging, either to estimate the trend weights or to estimate the Kriging weights in order to get our universal Kriging estimate. So this it's a fairly okay procedure. There's an additional problem, which is that our OLS estimates often require that our residuals are that once we've done OLS, our residuals are no longer correlated, and that's not necessarily the case, right? Because we have this here. So, so essentially what people have proposed is to do an additional GLS step where we use then using the variogram of the residuals to calculate a generalized least square estimate of the trend. My personal experience with that is it changes things a little bit, but I think in the grand scheme of things, given all the uncertainties we have, and particularly the difficulties often in interpreting variograms, I think that kind of difference is not going to show up as very dramatic. So this one-step procedure here, I find is quite efficient. If you're in SGEMS, you will have to do that outside of SGEMS. So you'll have to estimate that trend in another form, and then import the residual data and can calculate computer variograms and solve universal Kriging. So here's some examples. For example, in this case, you notice that we don't see much complicated trend in our data, so we use a simple linear model for our regression for the mean. So so we do ordinary least squares, which basically means we're estimating those three values raised from this set of data. We get this function, so we see, notice a little bit trending in the y, but most of the trend is in the x direction. There's a special case which is called Kriging with external drift. In that case, the trend is rather complicated, cannot written as these simple functions, but we may have a way of estimating the trend with another method. So here we're using a spline's function, and in that case, now we have what is called this drift function. So we replace this, in this case, we have only one function, which is exactly this function. So this function is known at every single location and becomes a drift function. One other application of this is to use, for example, a secondary data drift function. So in that case, for example, you may have such as in the groundwork case we're dealing with, so this may be your electrical resistivity data. And so we can use that electrical resistivity data, which is a different unit than the observations that we are trying to estimate, for example, porosity. And we use this in the drift. What we're doing is we're calculating the residual, and then we do universal Kriging with this drift function, and that will then show up indeed as including that kind of information. So in that case, the secondary data is used as a mean. That ignores some aspects of the secondary data, and that's something that we'll come back to when we talk about co-creating. Okay, so here's a worked out example. So we have our unknown truth, we have our data. This is the variogram of this information, you know, this non-stationarity showing up. So we model that trend, the OLS trend, and we subtract it and we calculate the variogram, and we have now the variogram of the residuals. So you notice that the residuals are still correlated. It's not that they suddenly become uncorrelated. And then we perform our universal Kriging estimate, and this is our universal Kriging estimate from this data with this previous trend function.